So, we are earlier discussing combination of basic solutions of Laplace equation, and the first combination that we considered, if you remember, is a point source in uniform stream, and we saw that the resulting flow represents flow over a semi infinite fairing, a body which is closed at one end, but open at the other end. It is closed near to the source, but it is open at the other end. So, next combination that we will look for is almost similar, only we will add one sink to it, that is, it is now uniform flow plus a point source plus a point sink. Source and sink are of equal strength. Basic solutions or as you can see that the basic solutions, that is source, sink, they are all singular at r equal to 0 or at the position of the source or sink, neither the potential nor the velocity are defined, and hence they are called singular solutions. So, this time we will consider now a uniform stream plus a point source or infinite line source, a two dimensional point source plus a two dimensional point sink, and for convenience we will take source and sink are of equal strength. Once again, let us consider a uniform stream from left to right with free stream velocity u infinity and a source and sink. The source strength is m and the sink strength is minus m. And let us consider the distance between the source and sink be 2 L. We will choose our origin at the midpoint on the line joining source and sink. The origin is here at the midpoint. So, this is our x axis and this is our y axis. So, what will be the combined potential for this flow? Potential for this flow, potential function and stream function for this flow. potential function and stream function for this flow. Yes, what will be the potential function and stream function for this flow? Potential function at any point x y. Yes, please tell me what will be the potential function at any point x y. It is just sum, there is nothing special in it. Add 3 potential function and you will get the combined potential function. Potential due to uniform stream along x axis u infinity x, okay, that u infinity x, then potential due to the point source at point x y, yes, m by 2 pi log r. But what is this r? Distance from point source to the point x y. Okay. Now, in this case, and the same potential function for sink also, but the two distances will be different because source and sink are placed at different point. It is not exactly the position vector of that point, it is that r minus r 0, where r is the position vector of the point where you are finding the potential function and r 0 is the position vector of the source or sink. So, write it now in this fashion, m by 2 pi say log r 1 and the other one is m by 2 pi log r 2. Okay. What is r 1? Can you tell what is r 1 or r 1 square? It is not simply x square plus y square, it is x plus l whole square plus y square. Yes? And similarity R 2 is and what about this psi? The stream function, stream function due to the uniform stream is u infinity y, and the other two m by 2 pi theta or theta 1. Yes, stream function for point source. But what will be that theta in this case? M by 2 pi, say in terms of x and y, theta you express theta in terms of x and y. Tan inverse y by x plus L, y by x plus L, and the other one is is it? Okay, let us work with the velocity. Of course, you can now evaluate using any of the two. Let us concentrate on psi. Let us concentrate on psi. You can combine these two terms, those two tangent inverse term you can combine. What will be the result? See what is the representation. Let us take the sink and source separately. This is source and sink, say this is the point P x y, this is the axis, this is your x axis, this is the y axis. So, this is what is that angle theta 1, which is tan inverse this. And this is the angle theta 2. So, if you combine theta 1 m by 2 pi theta 1 minus theta 2. Okay. If you write in terms of theta 1 and theta 2, this term is m by 2 pi theta 1 minus theta 2, and theta 1 minus theta 2 is this angle. So, in that form we can straight away write m by 2 pi, let us say this angle is beta, then this term represents m by 2 pi beta. In terms of tan inverse, you can combine two tan inverse term or otherwise write what is beta using x, y and L. This will come as u infinity y minus m by 2 pi tan inverse 2 L y by x square plus. So, this is the combined stream function for this body. Now, do we have a closed streamline? Is this a closed curve? We know, but for a constant value of psi, this represents a streamline. Okay? You choose a value constant for psi, it is a streamline. Even you can plot it by choosing different values of psi as a constant. Let us say the 0 streamline, where psi is 0. If we consider that 0 streamline, then this is 0. Is this a closed curve? Psi equal to 0. This curve may not be that familiar, but as it happens it is a closed curve. The 0 streamline again is a closed curve which represents a Rankine oval, an oval shaped body usually called as Rankine's oval. and we can say that this combination, a uniform stream, a source and sink of equal strength separated by distance L or distance 2 L, represents flow past a Rankine shaped oval. As you had that uniform stream and a point source represents flow over a semi infinite fairing. In this case, it represents flow over a Rankine oval. And you see this, the point source and point sink now within that oval. So, that is not in the flow field. The oval we can now think of as solid oval. So, there is no flow or nothing within that oval, and outside flow there is no singularity or nothing. It is a purely inviscid irrotational flow, incompressible irrotational flow or ideal flow. So, there is no extension, no rotation in the flow field. Whatever extension, rotation that we incorporated, that remain within the body. So, practically that does not exist in the flow as far as the flow is concerned. If you plot this curve, you will see that this is a closed curve, not like the semi infinite fairing, where it is closed at one end, but open at the other end. It continues up to infinity, never closing. In this case, it closes, it is a closed body. There is no practical interest. See, there will be no flow inside the oval. We are interested only flow outside the oval. Think about a solid oval, then of course, there is no flow, or even if it is a hollow oval, there is no flow inside. We are not interested in it. We are not interested in anything in it. This is the closed body, let us say, this is the oval, and I have represented only one streamline just to show. Similarly, you can plot as many streamline as you want for different constant of psi. They are now very easy to plot. Choose a value of psi, a constant value of psi, or go on increasing psi in an uniform rate. You can plot as many streamline as you like, and you can see what the flow looks like. Okay, what is the maximum thickness of this body? You can see it from here that the body is both symmetric with respect to x and y axis, and the maximum thickness is of course at y axis, that is at x equal to 0. So, what will be the maximum thickness of the body? How much? Find y when at x equal to 0. u infinity y max okay. The actual thickness will be 2 times the y max. Where will be the stagnation points? Stagnation points means points where the velocity is 0, flow velocity is 0.
We can get an easier formula if we substitute x equal to 0 in the complete expression of stream function. So we can get another formula.
Okay. So, these are the formula which will be used to find eventually m, the value of source strength. Remember, in a practical problem, let us say that you are given an oval and you have to find the flow. You know this much, that the flow over an oval is superposition of a uniform stream plus a source and sink pair of equal strength. But for a given oval, you have to find what would be the source and sink strength. That is what is unknown to you for the practical problem, and that source strength can be obtained say from this formula or something like this, or the actual thickness will be known to you. Okay, find the stagnation points. It is very easy to say from here that the stagnation points will be here, here and here. these will be the two stagnation points. Of course, you can find the velocity, write the expression for velocity, and from there also you can find it, but sometime from the problem itself you can straight away say that okay, this will be what it is. So, that these will be the stagnation point, these and these. Okay. So, locate those stagnation point. So, this part I am writing without finding the velocity, that the stagnation points are at x equal to say plus minus a 0 and y equal to 0. Remember, this is not the location of source. So, x, the stagnation point will not be at x equal to minus L and plus L. Eventually, this a 0 will be larger than the source, will be somewhere here say perhaps, and sink will be somewhere here again. And this will be required to find that L. Look again, if you have the oval with you, you know what is this a 0. That a 0 is known to you. What is not known to you is L. What should be the separation of source and sink, that will give this flow. So, that can be obtained from here. This will give a relationship between a 0 and L, and since a 0 is known to you, the oval will be known to you. So, what will be a 0? Find the velocity components. Find the velocity components. What is the velocity component u? Anything you want, you can use either phi or psi. Say we are working in terms of psi, so it would be easier to find it in terms of psi. D psi dy. U infinity, then differentiate that tangent function. How much is that? 1 by 1 plus
of x square plus y square minus
Hmm?
x square.
Oh, this is square. This. And what about the other component? What will be the other component? Give me that final expression. What is V?
2x y ln
2
x y ln
2 x y
ln
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 lm
upon pi in the brackets x square plus y square minus one square whole square plus 4
plus a separate term or on the denominator itself?
in the denominator plus 4 l square y square
4
l square y square.
L square y square.
So pi is outside the bracket.
Pi I have written out. Achha. You mean say this. This. See, it is not very important. I could have mentioned here, at least for this purpose, as far as finding the stagnation point is concerned. You can see that this V component is always 0 on the x axis. As long as y is 0, V is 0. So, for stagnation point, what we need is we need to make u 0, that is all. V is 0 at all point on the x axis. So, to find the stagnation point, finding V was not necessary. We could have straightaway said that the V will be 0 on the x axis, at all point on the x axis. Then at the stagnation point, that is when x is plus minus a 0, u is 0. So, find out what is this. and this gives so, if we take now these two relations, this and that earlier thickness formula that we had, using these two we can find what are M and L, that is the source strength and the separation between the source and sink to generate a practical oval or real oval. We can find the pressure distribution at any point or pressure at any point, or in particular the pressure distribution on the surface of the oval by the simple application of Bernoulli's equation. We can use the Bernoulli's equation at one point far away from the body, that is at infinity, and at one point on the body surface or anywhere in the flow field, because this flow is rotational flow. So, we can apply the Bernoulli's equation at any point. The 2 points need not be on a streamline, we can apply it anywhere. So, if we apply it between a point at infinity where the pressure is P infinity and the free stream speed u infinity. So, that Bernoulli's equation at infinity represents P infinity plus half rho u infinity square, and another point on the body surface P plus half rho say q square, if q is the velocity on the body surface, which of course we can find the velocity on the body surface from this general relation for u and v satisfying x and y for the body. Of course, as you can see that the expression for u and v are not very short or very handy expression, they are quite unwieldy. So, we will not try to write those equations, but this is what it can be done straight away. If we have numbers, then we can get a very small number and can use it, but they are not that convenient to handle in an analytical fashion. So, we will not do it now. Can you say what type of force this Rankine oval will experience because of this pressure distribution? Whatever the pressure distribution will be, even though we are not writing the expression, can we say what type of pressure or force this Rankine oval will experience because of this flow? Any guess? Any guess? See, without doing anything or without using any of these expressions, see to it this way, that to the flow which is coming along the x axis of the oval, see this flow will see this is a symmetric body. To the flow, this body will appear just a symmetric body, symmetric with respect to x axis, as well as in this case it is symmetric with respect to y axis also. That means, the body has a symmetry both top and bottom as well as front and rear. So, the flow will also be symmetric. In this case, with respect to the flow, the body is symmetric. So, the flow is symmetric, the velocity field, pressure field, everything will be symmetric. a perfect symmetry, both front and rear, that is the front half of the body, this front half of the body and the rear half of the body. Velocity distribution and pressure distribution is perfectly symmetric. Again the top half of the body and bottom half of the body, again velocity distribution and pressure distribution will be symmetrical. So, now let us consider this top and bottom. If the pressure is symmetric with respect to this top and bottom, so what will be the net force in that direction or in the y direction in this case? 0. Again it has a front and rear symmetry, again the force in the x direction will be 0. So, this pressure distribution will not create any force, not impose any force on the body, neither a lift force nor a drag force.
How the pressure is symmetric in rear and front side? Means uniform stream is coming from one side only.
Uniform stream is coming in from one side only, but the body shape and this inviscid, derotational, incompressible nature of the flow is making the flow perfectly symmetric, both with respect to top and bottom. The velocity is symmetric, that you have no doubt about that. That part you are convinced that the velocity is symmetric. Velocity is symmetric. If the velocity is symmetric, why should the pressure will not be symmetric? Because it has to satisfy that condition P infinity half rho infinity square, which is happens to be a constant, is P plus half rho v q square. If that q is symmetric, P has to be symmetric, it is a constant. Of course, as I said that the writing an expression for P is quite unwieldy expression. So, that is what we are not doing. Of course, it can be done, but it will be a very lengthy, very complex equation. So, this is little absurd, no, that if there is a oval and there is a flow, then there is no force acting on it. It is a little absurd. Perhaps lift can be expected, that okay, there is no lift force acting, but no drag is also acting, that is a little difficult to believe, because that type of situation never occurs. There is no lift or practically no lift, that is a quite common situation, but no drag, that never happens, but it gives that. Okay. We will now move to a different situation, but which is very close to it. That is, we will now bring the source and sink close together, so close that they form what we have called earlier a doublet. That is, the separation between source and sink approaching to 0, and simultaneously the strength of the source and sink is increasing. So, that the product remains a fixed number, that m l or m into 2 l, that product as l approaches 0 and m approaches infinity, that product still remains the same, which we call the doublet strength mu. So, that 2 l m will be mu. In those expressions, that 2 l m will replace as mu and what we will get is flow due to a uniform point doublet in a uniform stream, and since both source and sink are approaching each other, they will approach when they reach to that origin. We kept the origin between midway between the source and sink. So, now we are approaching them. So, in the limiting case, the doublet will be placed at the origin. So, the resulting flow will now be in the limiting case flow due to a point doublet placed at origin in a uniform stream. So, that is what we will next consider. Again the point doublet we are meaning 2D. So, not a 3D point or not actually point doublet, it is a infinite line doublet. But before we start writing this potential and stream function, of course, by now you can do it easily, the approach is same. We will bring something to your notice. Look, the first problem that we consider, a point source in a uniform stream. The resulting body is closed at one end, the end near to the source. The body has a thickness and it is open at the other end. Now, see that when we placed a point sink on the other side, it closes on that other side also. The body has still a thickness. This gives a general idea or a modeling philosophy that if we want to close a body, if we want to have a closed body, then we must have source sink combination, not only source or sink, we must have source and sink combination such that the total strength is 0, total source and sink strength is 0. Also, this body will have a thickness. So, if we want to have a thick closed body, any body which has certain thickness and the body is closed, then we must have a source sink combination such that the total strength is 0. This is a general principle. A combination of source and sink, I mean number of sources and number of sink such that the total strength is 0, then all streamlines which emanate from the source will terminate at the sink, and there will be one streamline which will enclose all these source and sink. Okay. There will be one streamline which will enclose all these source and sink, which will represent a body. This body will have a thickness. It can also be not a discrete source and sink, but a continuous distribution of source and sink. We will call it continuous distribution of source only, such that its total strength is 0. Sink we will not mention as a differently sink, we will just mention on source, a continuous distribution of source, so that its total strength is 0, meaning that source is made up of source and sink both. This will be useful later on. So, when you have a point doublet, doublet also has a net source strength 0. So, here also we are, or we should have, or we will have again a closed body. And what body we will get, that is also I think quite easy to guess. That what will be that limiting form of oval when the tail approaches 0? It will be a circle. And if the cross section is circle, the body is a cylinder, infinite cylinder. So, a point doublet in an uniform stream will represent flow past a infinite circular cylinder.